Smart pointers. A pointer is a general concept for a variable that contains an address in memory. This address refers to, or points at, some other data. The most common kind of pointer in Rust is a reference, which you learned about in Chapter 4. References are indicated by the ampersand symbol and borrow the value they point to. They don't have any special capabilities other than referring to data. Also, they don't have any overhead and are the kind of pointer we use most often. Smart pointers, on the other hand, are data structures that not only act like a pointer, but also have additional metadata and capabilities. The concept of smart pointers isn't unique to Rust. Smart pointers originated in C++ and exist in other languages as well. In Rust, the different smart pointers defined in the standard library provide functionality beyond that provided by references. One example that we'll explore in this chapter is the reference counting smart pointer type. This pointer enables you to have multiple owners of data by keeping track of the number of owners, and when no owners remain, cleaning up the data. In Rust, which uses the concept of ownership and borrowing, an additional difference between references and smart pointers is that references are pointers that only borrow data. In contrast, in many cases, smart pointers own the data they point to. We've already encountered a few smart pointers in the book, such as string and vect in Chapter 8, although we didn't call them smart pointers at the time. Both these types count as smart pointers because they own some memory and allow you to manipulate it. They also have metadata, such as their capacity, and extra capabilities or guarantees, such as with string, ensuring its data will always be valid UTF-8. Smart pointers are usually implemented using structs. The characteristic that distinguishes a smart pointer from an ordinary struct is that smart pointers implement the deref and drop traits. The deref trait allows an instance of the smart pointer struct to behave like a reference, so you can write code that works with either references or smart pointers. The drop trait allows you to customize the code that is run when an instance of the smart pointer goes out of scope. In this chapter, we'll discuss both traits and demonstrate why they are important to smart pointers. Given that the smart pointer pattern is a general design pattern used frequently in Rust, this chapter won't cover every existing smart pointer. Many libraries have their own smart pointers, and you can even write your own. We'll cover the most common smart pointers in the standard library: boxt for allocating values on the heap, rct, a reference counting type that enables multiple ownership, reft, and refmut, accessed through refcellt, a type that enforces the borrowing rules at runtime instead of compile time. In addition, we'll cover the interior mutability pattern, where an immutable type exposes an API for mutating an interior value. We'll also discuss reference cycles, how they can link memory, and how to prevent them. Let's dive in. Using boxt to point to data on the heap. The most straightforward smart pointer is a box, whose type is written boxt. Boxes allow you to store data on the heap rather than the stack. What remains on the stack is the pointer to the heap data. Refer to Chapter 4 to review the difference between the stack and the heap. Boxes don't have performance overhead other than storing their data on the heap instead of on the stack, but they don't have many extra capabilities either. You'll use them most often in these situations: when you have a type whose size can't be known at compile time, and you want to use a value of that type in a context that requires an exact size; when you have a large amount of data and you want to transfer ownership but ensure the data won't be copied when you do so; when you want to own a value and you care only that it's a type that implements a particular trait rather than being of a specific type. We'll demonstrate the first situation in the Enabling Recursive Types with Boxes section. In the second case, transferring ownership of a large amount of data can take a long time because the data is copied around on the stack. To improve performance in this situation, we can store the large amount of data on the heap in a box. Then only the small amount of pointer data is copied around on the stack, while the data it references stays in one place on the heap. The third case is known as a trait object, and Chapter 17 devotes an entire section using trait objects that allow for values of different types just to that topic. So what you learn here, you will apply again in Chapter 17. Using a box T to store data on the heap. Before we discuss this use case for box T, we'll cover the syntax and how to interact with values stored within a box. Listing 5.1 shows how to use a box to store an I32 value on the heap. Let B equal box : new 5. Print line B equals placeholder B. We define the variable B to have the value of a box that points to the value 5, which is allocated on the heap. This program will print B equals 5. In this case, we can access the data in the box similarly to how we would if this data were on the stack. Just like any owned value, when a box goes out of scope, as B does at the end of main, it will be deallocated. The deallocation happens for the box stored on the stack and the data it points to stored on the heap. Putting a single value on the heap isn't very useful, so you won't use boxes by themselves in this way very often. Having values like a single I32 on the stack, where they're stored by default, is more appropriate in the majority of situations. Let's look at a case where boxes allow us to define types that we wouldn't be allowed to if we didn't have boxes. Enabling recursive types with boxes. At compile time, Rust needs to know how much space a type takes up. One type whose size can't be known at compile time is a recursive type, where a value can have, as part of itself, another value of the same type. Because this nesting of values could theoretically continue infinitely, Rust doesn't know how much space a value of a recursive type needs. But boxes have a known size, so by inserting a box in a recursive type definition, you can have recursive types. Let's explore the cons list, which is a data type common in functional programming languages as an example of a recursive type. The cons list type we'll define as straightforward except for the recursion. So the concepts in the example we'll work with will be useful anytime you get into more complex situations involving recursive types. More information about the cons list. A cons list is a data structure that comes from a Lisp programming language and its dialects. In Lisp, the cons function, short for construct function, constructs a new pair from its two arguments, which usually are a single value and another pair. These pairs containing pairs form a list. The cons function concept has made its way into more general functional programming jargon. To cons into y informally means to construct a new container instance by putting the element x at the start of this new container, followed by the container y. Each item in a cons list contains two elements, the value of the current item and the next item. The last item in the list contains only a value called nil without a next item. A cons list is produced by recursively calling the cons function. The canonical name to denote the base case of the recursion is nil. Note that this is not the same as the null or nil concept in Chapter 6, which is an invalid or absent value. Although functional programming languages use cons lists frequently, the cons list isn't a commonly used data structure in Rust. Most of the time, when you have a list of items in Rust, vect is a better choice to use. Other more complex recursive data types are useful in various situations, but by starting with the cons list, we can explore how boxes let us define a recursive data type without much distraction. Listing 15.2 contains an enum definition for a cons list. Note that this code won't compile yet because the list type doesn't have a known size, which we will demonstrate. Enum list, two variants, cons with associated data, i32, and list. The variant is nil. Note, we're implementing a cons list that holds only i32 values for the purposes of this example. We could have implemented it using generics, as we discussed in Chapter 10, to define a cons list type that could store values of any type. Using the list type to store the list 1, 2, 3 would look like the code in listing 15.3. Use crate lists cons nil function main let list equal cons takes 1 and cons taking 2 and cons taking 3 and nil. The first cons variable holds 1 and another list value. The list value is another cons value that holds 2 and another list value. The list value is one more this list value is one more cons value that holds 3, and a list value, which is finally nil, the non-recursive variant that signals the end of a list. If we try to compile the code in listing 15.3, we get the error shown in listing 15.4. The error shows this type has infinite size. The reason is that we've defined a list with a variant that is recursive. It holds another value of itself directly. As a result, Rust can't figure out how much space it needs to store a list value. Let's break down why we get this error in a bit. Let's break down why we get this error a bit. First, let's look at how Rust decides how much space it needs to store a value of a non-recursive type. Computing the size of a non-recursive type. Recall the message enum we defined in listing 6.2 when we discussed enum definitions in Chapter 6. Enum message, 4 variants: quit, move, which is a struct with 2 fields, x and y, both of type i32, write, which has associated data of a string, and change color with an associated tuple of i32s. To determine how much space to allocate for a message value, Rust goes through each of the variants to see which variant needs the most space. Rust sees that message quit doesn't need any space. Message move needs enough space to store 2 i32 values, and so forth. Because only one variant will be used, the most space a message value will need is the space it would take to store the largest of its variants. Contrast this with what happens when Rust tries to determine how much space a recursive type like the list enum in listing 15.2 needs. The compiler starts by looking at the cons variant, which holds a value of type i32 and a value of type list. Therefore, cons needs an amount of space equal to the size of an i32 plus the size of a list. To figure out how much memory the list type needs, the compiler looks at the variants, starting with the cons variant. The cons variant holds a value of type i32 and a value of type list, and this process continues infinitely as shown in figure 15.1. Using boxt to get a recursive type with a known size. Rust can't figure out how much space to allocate for recursively defined types, so the compiler gives the error in listing 15.4. But the error does include this helpful suggestion. Insert indirection. In this suggestion, indirection means that instead of storing a value directly, we'll change the data structure to store the value indirectly by storing a pointer to the value instead. Because box T is a pointer, Rust always knows how much space a box T needs. A pointer size doesn't change based on the amount of data it's pointing to. This means we can put a box T inside the cons variant instead of another list value directly. The box T will point to the next list value that will be on the heap, rather than inside the cons variant. Conceptually, we still have a list, created with lists holding other lists, but this implementation is now more like placing the items next to one another rather than inside one another. We can change the definition of the list enum in listing 15.2 and the usage of the list in listing 15.3 to the code in listing 15.5, which will compile. Enum list cons with an associated tuple of an i32 and a box of list and nil. Use crate list cons and nil. Function main let list equal cons1 and box new cons 2 and box new cons 3 and box new nil. Lots of parentheses. The cons variant will need the size of an i32 plus the space to store the box's pointer data. The nil variant stores no values, so it needs less space than the cons variant. We now know that any list value will take up to the size of an i32 plus the size of a box's pointer data. By using a box, we've broken the infinite recursive chain, so the compiler can figure out the size it needs to store a list value. Figure 15.2 shows what the cons variant looks like now. Figure 15.2, a list that is not infinitely sized because cons holds a box. Boxes provide only the indirection and heap allocation. They don't have any other special capabilities like those we'll see with the other smart pointer types. They also don't have any performance overhead that these special capabilities incur, so they can be useful in cases like the cons list, where the indirection is the only feature we need. We'll look at more use cases for boxes in Chapter 17 too. The box type is a smart pointer because it implements the deref trait, which allows box values to be treated like references. When a box value goes out of scope, the heap data that the box is pointing to is cleaned up as well because of the drop trait implementation. Let's explore these two traits in more detail. These two traits will be even more important to the functionality provided by the other smart pointer types we'll discuss in the rest of the chapter.